Okay, so our next question is about two ice skaters pushing each other away. Their total momentum, we know straight away, is going to be unchanged because momentum is conserved. So the answers straight away are limited to A or B. The total kinetic energy, well, if we think about it initially, we know that kinetic energy is given by a half mv squared. Initially, the velocity is 0, so there's going to be 0 kinetic energy. But afterwards, each skater is going to be moving with a certain velocity, so their kinetic energy is both going to be greater than 0, so the kinetic energy must be increasing. This must mean that the answer is A for question 3. For question 4, we're having to work out the Earth's speed as it moves around the Sun. And we're given a couple of pieces of information that are going to help us out with this. But the first thing we've got to notice is that the radius of orbit is given to us in kilometres. We mustn't get put off by this because we must be remembering that we use SI units for our calculations. So the radius is going to be 1.5 times 10 to the power of 11 meters. That's 1,000 times more than this number because this is in kilometres. Now that we've avoided that particular pitfall of the examiner, we should be in a good position to get the Earth's approximate speed just by looking at the formula sheet. We know that the velocity for circular motion is given by 2 pi r over capital T. That's the distance all the way around the orbit divided by the time taken for one complete orbit. 2 pi r is really easy. We've got already r, and we know what 2 pi is. T is going to be not too bad to calculate as well because we're talking about the Earth here. Again, we need to remember that we've got to calculate this in SI units though. The time taken to go around the Earth is to go around the Sun rather is going to be 1 year. So we need to calculate the amount of seconds in 1 year. So this is going to be 2 pi times the radius, which is 1.5 times 10 to the 11. We're going to divide that by the time period, which is going to be 365.25 days. Multiply that by the number of hours in a day, which is 24, the number of minutes in an hour, which is 60, and the number of seconds in a minute, which is also 60. And if we run that through a calculator, we should get an answer hopefully fairly similar to one of the 4 options that we have here. So it's going to be 2 pi times 1.5 times 10 to the 11. Divide that by 365.25 times 24 times 60 times 60. And that answer gives us 29,865.3 blah blah blah. So it's pretty much 3 with 4 zeros, which is 3 times 10 to the 4 meters per second. The answer to question 4 is going to be D. Question 5, we were asked about a particle moving in a circular path at constant speed, and we're given 4 statements. We've got to work out which one is correct. Well, statement A is definitely going to be false. It says the velocity of the particle is directed towards the centre of the circle, but we should know, hopefully, that when we have an object moving in circular motion, the velocity is moving at a tangent to the path. Here's our radius here. So our velocity at any given time is going basically in 90 degrees to the radius. It's going tangentially to the circle. It's certainly not going into the circle, otherwise it'd move towards the centre. You will know that because if you spin something around your head and let go of it, it will fly off in a straight line in that direction. B, it says there's no force acting on the particle. That can't be right either, because if there was no force, it would obey Newton's law of motion, which is to say that an object with no force acting upon it, or no resultant force anyway, moves at a constant speed in a constant direction. This object is not going in a constant direction, it's changing its direction constantly. There must be a force applied to make it do that. Again, you'll know this because if you've seen something trying to go around in a circle and that force that's pushing it in is taken away, it will fly off. So if you try and go around a corner at high speed in a car and there's not enough friction to keep you going in that circle, you're going to find that you can't go in that circle anymore. You start flying out to the side. Statement D, the particle has an acceleration directed along a tangent to the circle, that would be along this direction here. That is also definitely false. We know that the acceleration is directed inwards towards the centre. We also know that Newton's law is F equals ma, and these two are vectors, so the force is in the same direction as the acceleration. This is the centripetal force we're talking about. The centripetal force is acting in this direction as well, so towards the centre of the circle. So that one can't be right. There's only one that is remaining, and that's going to be C. There's no change in the kinetic energy of the particle, and that's definitely true. Kinetic energy of the particle, Ek, is equal to half mv squared. The velocity here, or the speed rather, is going to be constant. The velocity technically isn't, because it's changing direction, but the size of this, which is what we're interested in for the kinetic energy, is going to be constant because it's moving at a constant speed. So its kinetic energy has got to be constant. So the answer to question 5 is going to be C.